Hi everybody, welcome to the lab. Got a lot of fun stuff for you today, but I want to start off with a demonstration. I realized that I have a curve tracer in the lab now and that I could demonstrate something to you in a way that you probably haven't seen before. So let's take a look at that. This is a 2SK 182ES, and if you watched the last lab hangout, then you know why this device doesn't look very linear here. And this is the same 2SK 182ES, but now you notice it looks different. The spacing between the traces looks a little more uniform, and maybe this is a more linear device. So what's the difference? What have we done? Well, the difference is I've inserted a 1 ohm resistor in series with the source of the SIT. And so let's talk about what that does. Okay, so let's talk about what's going on in that demonstration. Here we have a set of imaginary IV curves for an imaginary part. And you can see it's pretty idealized, but we can still get the characteristics for this part from the IV curves. And I'll start with the drain resistance, right? The drain resistance is a change in plate voltage over the change in plate current. So in this case, 10 volts over an amp and a half gives us 6.67 ohms. The mu, or the amplification factor, is the change in plate voltage over the change in gate voltage. And that's 8 over 2 in this case, which gives us a mu of 4. And the transconductance, which is a change in plate current over a change in gate voltage, is 1.2 over 2, or 0.6 Siemens, or mhos if you prefer. And we make those curves by each sweep of the curve tracer holds the gate voltage input the same while we sweep the drain to source voltage. Okay, and as we sweep the drain to source voltage, the current goes up, and we end up with that characteristic. What we're doing in the second part of the demonstration is we've inserted that 1 ohm resistor into the source of the transistor. And what's happening now is my curve tracer is giving, it's putting out that constant voltage input, but some of that is being subtracted, so this is negative feedback from the input, because we're dropping some voltage across that 1 ohm resistor. So the actual gate to source voltage that's being delivered to the part is changing as the current changes. And so what happens is I end up with this curve that's sort of leaned over like that. So let's take a look at the characteristics of this new composite part, we'll call it for now. The solid lines are the original curves, and the dotted lines are the curves for the new part, or the part with the 1 ohm source resistor. And you can see that the drain resistance has gone up. Right, we're leaning over more, so the drain resistance has gone up. It's now 9.33 ohms. The mu, and this is interesting, the mu is unchanged. It's still 8 over 2, gives us a mu of 4. But the transconductance is different now. 0.84 over 2 gives us 0.42 Siemens, or mhos. And that's because the mu and transconductance are actually interrelated, and they're interrelated by the drain resistance. So, in fact, GM is mu over the drain resistance. So, here's another view of that. This is just one. This is just one sweep, and you can see that the solid line is the original. The dotted line is with the 1 ohm source resistor, and in the original, the gate to source voltage, the actual gate to source voltage, of course, is the same throughout the sweep. And in the demonstration with the 1 ohm source resistor, that's the dashed line. You can see that the gate to source voltage is changing with the sweep. And so it changes the shape of those curves. And we call this, this is called series current feedback or series negative current feedback because we're subtracting from the input. It's negative feedback when we're subtracting from the input. It's positive feedback when we're adding to the input. And this is called current feedback because the error signal in this case is we're sampling the current through the load. Okay, and then we're feeding that back in series with the input. It's not in parallel with the input. It's in series with the input. So this is series current feedback. Okay, and so you can see that what we're really doing with feedback is we're changing the characteristics of those curves, and so you can decide for yourself whether that's a good thing or a bad thing. This is, I wanted to show you, that if I were to put the transistor without the 1 ohm source resistor into an amplifier, what sort of voltage gain I would get out of it. And so this is the normal gain calculation for a common source amp with a 12 ohm load resistor. We're going to keep that the same throughout this, and no source resistor using the original curves. Original curves, 12 ohm load resistor. Okay, and the voltage gain is mu times RD over big RD plus little RD. Big RD is the actual resistor on the drain, and little RD is the drain resistance itself. So 4 times 12 over 12 plus 6.67 gives us 48 over 18.67, which is 2.57, and 20 log gives us 8.2 dB. Okay, so that's the unaltered part in a common source amp with a 12 ohm load. Now we go to the normal gain calculation. We're going to use that same calculation for a common source amp with a 12 ohm load resistor and a 0.5 ohm source resistor. So this time we've got that source resistor in there in our amplifier circuit. Okay, and again the voltage gain, the calculation is different because we've got a source resistor in there now. So it's mu RD over big RD plus little RD plus big RS times mu plus 1. That's 4 times 12 over 12 plus 6.67 plus 0.5 times 5. That's the source resistor. 48 over 21.17 gives us 2.27. 20 log gives us 7.1 dB, right? So that's we would say that's about a dB of feedback, right? 1.1 dBs of feedback that we've applied with that 0.5 ohm resistor. Now, what's interesting is, or I think it's interesting anyway, is if we treat that transistor with the 1 ohm source that that I did on the curve tracer, if we put that in a black box with 3 terminals sticking out of it, and we treat it as a part, it's just inside a black box. We don't know if it has feedback or not, and we plug it into the original calculation. This is the gain calculation for a common source amp with a 12 ohm load and no source resistor. We're not going to use this formula, but we're going to use the composite curves. And look what we get when we take this out. 2.25 gives us 7 dB. Now, I mean, what's 0.1 dB between friends? You know, I just kind of eyeballed those curves. But what's interesting is from the standpoint of voltage gain, calculating the voltage gain, the part inside the black box behaves just like a real part. I can actually use those composite curves to calculate how what kind of out voltage gain this amplifier will give. And so that leads me to a philosophical / engineering question for you, which is if you take that transistor and you put a 1 ohm or a half an ohm resistor in the source and you put it inside a black box with 3 terminals sticking out, and I give that to you, and can you determine that there's feedback in there? And if so, how? And if not, what does that say about some of our paranoia about feedback? Is it really the feedback itself that's bad, or is it just the nature of the feedback? In other words, how does the feedback affect those curves, and does it affect those curves in a way that yields better or worse performance, right? So there you go. There's talk amongst yourselves, and we can discuss that on the forums. Okay, so I got a question about positive temperature coefficient from the last show, and so I set up a little demonstration to show you what that's all about. So take a look. Okay, I set up a little demonstration here of what is meant by positive temperature coefficient. And see, I've got a little circuit built up here, and there's a thermometer, indoor-outdoor thermometer on top of the heatsink, and the indoor temperature is the temperature here in the lab, and the outdoor temperature is the temperature of the case of that 2SK180 there, which is just attached to a temperature probe, which is stuck to the case with a glob of blue tack. And if we take a look at the power supplies, we're idling at about 1.52 amps, and that's been pretty steady. And we're at minus 6 volts gate to source. Okay, and we'll keep that minus 6 volts gate to source. And what we'll do is we will vary the temperature of the part, and I'm going to do that just by heating it up a little bit. You can see the temperature starting to go up. "55, 56. Now we'll look at the current. The current is just starting to creep up. 154, 155, 156, 157, and so on. And this will continue. Case is at about 67 degrees right now. And so when we
keep the gate voltage the same and we heat up the part and the drain current goes up, that is a positive temperature coefficient. So there you go.
Now I should mention that I was taking some readings, and the gate leakage current is pretty temperature dependent, and so that might be contributing to the positive temperature coefficient a good bit. So you want to check it out, you want to measure it, and if you need to, you got to use a smaller input resistor. You might have noticed that I had the Hammond inductor wired in the circuit in that demonstration, and that's because Paul asked me if I had tried out the Hammond 193V in the circuit, and I did, so let's check that out.
Okay, this is the inductor version of the 2SK180 amplifier. You can see I've got the Hammond 193V inductor wired in place of the light bulbs, and the operating point is about 38.2 volts, and if we go up here it's about 1.5 amps, and the total power supply voltage is 42 volts, and the gate to source voltage is looks like about 6 volts plus the or minus, I guess, the 1.5 volts that I'm dropping across the 1 ohm source resistor, so 7.5 volts. And the distortion looks like about 0.143% at a watt, and it goes to 7 or 8 watts, I guess. It may be 1.5% or something like that. So that's the inductor version of the 2SK 180.
Okay, by request, one last demo. Here's a low-tech way to test SITs.
All right, bonjour, Mr. Sound Happy in France. Sound Happy asked if he could test his batch of 2SK 182 ESs with simple lab equipment. And Nelson Pass responded with a procedure, and I'm going to demonstrate that here. You can see we've got a 1 k ohm quarter watt resistor there, and a 10 ohm 50 watt power resistor. It's not on a heatsink right now, so it's derated to 5 or 10 watts that way. And there's our SIT, and it's wired into this contraption like so. Our bench power supply is attached to the drain, and the source is attached to ground through that 10 ohm resistor, and the gate is attached to ground through that 1 k ohm resistor. And then what we do is, in this case, we're applying 12 volts to the drain, and then we measure the voltage across that 10 ohm power resistor. And you can see we got about 2.5 volts. And what that tells us is that our drain to source voltage is the power supply voltage minus what we're dropping across that resistor, which leaves us with 9.5 volts. The gate to source voltage then is minus 2.5 volts, and the drain current is 0.25 amps. And just for fun, I took another data point. This is with a power supply at 20 volts. And at 20 volts, we get 0.3 amps drain current. So we drop 3 volts across that resistor. So 20 volts minus 3 volts is 17 volts. The gate to source voltage then is minus 3 volts. And as I said, our ID is 0.3 amps. So there's a couple data points, and if we take a look at a picture of this actual part, you can see where those data points lie on the graph. So go ahead and measure up your parts and let us know what you get. Wasn't that fun?
Okay, now be safe and follow all your safety precautions when you do that. I've got a fire extinguisher in the lab and I wear safety glasses, so be careful. Okay, shout outs to Paul, Woody, Alexander, Gerd, and of course our fearless leader, Nelson Pass. All right, that's all for this time. I hope you enjoyed the show. I hope there was something useful for you in there. And please subscribe and give me your feedback and get all your cousins and uncles to subscribe. And just have fun and go build something.